for this protocol, they used a custom XOR encoding routine for all of the packets on the wire. So I reversed that out, and then I created an encoder. So now I can just draw out the protocol using the basic blocks and not have to worry about how it's encoded. At the end, I just tie this function to my data, and it's all taken care of.
We also have this concept of dependencies. This originally stemmed from this fuzzing framework a long time ago, about a year ago actually, was an attempt to fuzz SWF files. And SWF, that file format, is a pain in the ass because it has dependencies all over the place. So after scrapping that framework and starting up on this one, we did keep the dependency aspect of it, which is basically, in this case, what we're going to do is you're going to have, we declare an opcode, which is a short value. So then we declare a block after that. And in certain cases, we're going to want that block to be rendered. Say, for instance, if the opcode above that, during mutations, if that opcode is a 10, if that's what the render value is, then we're going to want to render that block with the string Aaron right there. For instance, if it's a 15 or 16, we would like to render the next one, which is a URL, and the next one is if it's not 10, 15, or 16. So the arguments that you can pass to a block like this, if you're dealing with dependencies, are you give it the dependency primitive, so that's the dep equals opcode. Then you give it the values, so dep values is 10, 15, or 16, and the comparison. So that is actually something that's going to be evaluated. For in this case, it's not equals. You can do equals, you can do less than, greater than, things like that. So at any given point, only one of these blocks is going to be rendered, and that depends on the value of the short opcode. This is very useful for certain protocols.
This concept of sizers, again, this is something that is necessary for doing block rendering. It's one of the things that Spike kind of introduced. So you apply a sizer to a block, and it dynamically calculates the size of that block. So if you have a protocol that's going to be like a TLV, you have a type, you have a length, and a value. As we're changing that value, as we're cycling through the different options for that value, we want that length to be updated so that the actual parsing of that TLV is correct, but then maybe in the parsing of that value later on down the line is where a fault is induced. And so by default, you don't fuzz a sizer. You want these sizers to be valid. But of course, you can turn this on as well. You can fuzz a sizer just as if it was an integer. And so we can do things like specify the length. I want to say it's a 4-byte length of this block. The endianness, again, the output format, binary, ASCII, whether or not it should include itself in the size count. And all this will kind of become clear when we pull up some real samples.
Yeah, basically, all these different representations are just to make it so you can take a complex protocol and very quickly, very easily represent it. Another thing that we do is checksums, which allow you to, this is very common in protocols, obviously, is just to throw a checksum for a certain block. So you associate a block, you say, I need the checksum, you point it at that block, it'll calculate the checksum and append it or prepend it, depending on where you put the checksum. You can give it an algorithm for CRC32, Adler, MD5, SHA-1, or any arbitrary function pointer, meaning you can actually define your own checksum routine and just point it to that function. You can do things like tog the endianness of that representation and other things.
Another concept also new to this framework, kind of advancing data generation, is the usage of repeaters. So if we have a block, we can use an sRepeat instruction to repeat that block a variable number of times. We can do from min to max, how often, how much a step it per iteration. And alternatively, we can tie it to a variable. So repeat this the number of times specified in some other integer that's being fuzzed. So if that integer goes up to 20, repeat this block 20 times. And this is useful, for example, there's been a couple of bugs in like a Microsoft Excel where the issue hasn't been in the parsing of like a single table entry, but if you had too many entries in the table. So if you have, in this case that I give, a table entry of the form type length string, I'm creating a block here. I just call it table entry. I've got a random, I've got a size. You can see this size is length 2 and describes the length of this next block that's being defined. That one just contains a simple string. And on the bottom, we're going to repeat it from 100 to 1,000, stepping at 50 every time. So if there was an issue with parsing too many entries in the table, we can represent that in this data representation format, which you couldn't do before.
So all the things we just previously went over are things that are currently built into the framework. This new thing is the one part where we start to get into the extensibility of the framework. We call this Legos, and it's basically allows the user to create complex types of their own definition. So email address, IP addresses, or whatever particular data structure that the protocol you're dealing with might itself define. So this is basically a library of data types that you can extend that Sully itself has. This example right here is creating a Lego called tag. So this could be XML tags, HTML tags, whatever other kind of tags are represented like this. This looks a little bit, it's not quite as easy to read as everything else because this is the part where you may be extending the actual framework itself. Using the framework is you don't have to really deal with this stuff, but you can see that we're calling push a few times, and that's actually pushing onto a stack that represents this data type. So first thing we're pushing is a delimiter, which is a bracket, and then a string, which would be the contents of that tag itself, and then an ending bracket. So that's a very generic way of representing a tag, and then in any future request that you're dealing with, you can just import Legos and import this tag specifically and use it for whatever you need, and Sully will take care of the fuzzing for it.
So like some of the Legos we have are like ASN1 types, email address, DNS host names, URLs, just things that you're going to be seeing frequently all over the place. And one of the ones we have that we broke last week is an IP address Lego, where depending on your testing environment, it'll update the IP address to either the client or the server. So if you're dealing with a protocol where the actual IP address of either the source or the destination is embedded in the protocol, it'll auto-update, and it'll fuzz it as well as, this dotted quad or however or binary format. So that's the data generation piece. The next piece of it is this whole session management concept. So first, an introduction to pgraph. Pgraph is just a Python graph abstraction library, and I originally wrote it for PyMay. It's just really easy to use. You launch Python, you say, okay, here's a node, connect these edges together, and you can render it in any of 3 different languages. You can do a GML, GraphViz, and UDraw. And the session class extends from this, and this is how we do this graph-based approach of building a fuzzer. Every request that we build is a node, and then we tie them together in a graph called a session. So one of the things you can do, I have a graph of this? Yeah. So we can register pre- and post-send callbacks to the graph. We can assign a callback to each edge. We can add multiple network targets in the session class. This is where we expose a custom web interface. We communicate with registered agents. And this is the class that's responsible for walking the graph structure and fuzzing at each level. And this is very tightly used in creation of drivers, which we'll give an example. So this concept of graph-based protocol representation is what gives us a lot of the powerful features. So in this example, I give, it's SMTP again. I promised I'd bring this up. So here's the root node where you can define a pre-send. So before I send anything, you can define a function to set the session up. So if I'm fuzzing DC RPC, I'm going to do an RPC bind. And that's an example I'm going to show in the trend. And then we've got a decision branch. We can either start off with an EHLO or a hello. Then we've got the mail from request, recipient to request, data request, and we have an optional post send as well. So if I'm managing the construction of a fuzzer, I can say, Aaron, I want you to really research the hell out of and write a mail from request. Cody, I want you to go and look at hello and EHLO and create requests for those. And they can go off and do their own research and come back, and we can tie it all together and do this full case fuzz. So for example, let's say we have a system where it's a challenge response, where we send out a packet with a challenge, we get a response back, and we need to use that response in the next packet, the next request. What we can do is we can define a callback function and assign it to the edge between the challenge response mechanism. And what that callback is going to get is it's going to get the next request that's going to go out, the request that just went out, and the packet data that came back and forth. So you can parse it, pull it out, and assign it into your next request, and essentially handle challenge response, previous packet specifies next length. And this is something that you could not do in other frameworks that you can do now. I remember Charlie Miller, who deserves huge kudos for really being a key editor on our book. Him and I were kind of going back and forth on the pain points of fuzzing, and this was before I had shown him this, and it was kind of uplifting for me to hear from him saying, "Oh, that's cool! I can't believe you thought about this, XYZ 1, 2, 3. I'm excited to start using this thing." Another thing to mention here is, I forget what bug it was, but it was an Ipswitch where there was an overflow in the parsing of email addresses with a certain form in, I think, mail from. But depending on whether or not you came in from an EHLO or an HELO, it would or would not show itself. So the bug was only if you went down one path versus another. And so the benefit of doing things like this is we can create these arbitrarily complex protocols, and the fuzzer takes care of it all for us. Every path, every node is going to be fuzzed individually. So it would start off, for example, and it would go through every iteration of EHLO. When that's done, it's going to revert it back to the valid form that you gave it. Then it's going to send, pre-send, valid, and then start fuzzing mail from. When that's done, it'll go pre-send, valid, valid, fuzz, recipient 2, all the way through to the end. And then it'll go the other way around, pre-send, fuzz, pre-send, valid, fuzz, and give you every single path, every single request. This is a screenshot, and you'll see the real version of it, of the web interface. It's really simple and bare bones. It's going to tell you what's our total progress, what's the progress of the current request. It's going to give you a list of all the crashes or the faults that were detected. If you click on this link, it'll pull up the actual crash dump. On the right-hand side, which is cut off in the screenshot, is a link to the PCAP. So if you want to just pull up the PCAP to take a look at it, you can do that as well. You can pause and resume the fuzzing. And actually, because our session has a built-in state saving to disk, you can stop fuzzing, shut everything down, and then start it up a week later, and it'll pick up right where it left off. The next piece that we're going to kind of zoom in on and explain is the agents piece.
So agents are another extensible part of the framework. Right now we have a few defined. Basically what they are little programs that communicate over what we call PET-RPC, which is just a way to remotely call any of the functions, just a simple form of RPC. I'm going to go over a few of the ones that we've developed so far. The first one is we call netmon. This can be run either on the same machine that you're fuzzing from or on the target system. And what it does is it uses a PCAPI and IMPacket to save all the packets in every single test case bidirectional to disk. It allows you to do BPF filters, so you can say, source or desk port this, and it'll just save everything. Depending on the log level, you can have it, print more debugging output and things like that. The next one we have is our process monitor. This one is probably the most interesting. It is a PyDebug-based agent that you run on the same system that that the target software is on, and it'll attach and it monitors the health of the actual process. So while you're fuzzing, if an access violation occurs, this will dump all context data. It will save it in what we call a crash bin, which is just a marshaled data format, which will save all of the context data. It'll save the current instruction. It'll save the SEH stack, all that kind of stuff. And there's a lot of other things that you can do with this agent. Because it's written in PyDebug, which is written in Python, which is scriptable, you can do all sorts of different things in this one. The next agent that we have is the VM control. This one is generally going to be run from the system you're fuzzing from, and it allows you to revert the VMware image to a known good state. So if a access violation occurs, the process monitor, which is attached to the process, notifies the VM control. The VM control will reset it to a known good state. Meanwhile, you're going to have the saved PCAPs, you're going to have the saved crash bins, and the web interface is going to be updated, showing you all that and having links to all the information you would need. This one's pretty straightforward. It has an interactive mode that we recently added that just lets you basically just say VM control -I, point it to your VM run, point it to your VMX, and you're ready to go. And Pedram's going to go over the drivers now.
So the driver is really where it all comes together. You take your requests out of the library, you instantiate a session, you instantiate some targets, you describe them, you connect it to agents. This is where you define your pre and post sends. And it's really free form, though most of them will follow the same structure. And we're going to talk about how, or later in the future development, we're going to attempt to make a GUI around this. So here's an example driver. I'll zoom in. And actually, this is the driver that was used to discover a fault in Trillion in its